Okay, welcome back everyone. Let's continue with the second part of the lecture. So before the break, we were studying this fundamental lemma by Willems and co-authors, which gave us the conditions under which this rank condition on the state input Hankel matrix holds. Okay. Is it on now? Maybe I should put it a little bit higher. Is it okay now? Yes? Okay, great. So I want to show you the proof of just item 1 of the fundamental lemma now. So for the proof, I need some notions of controllability. So first I define the reachable subspace as the image of this controllability matrix. And I use a notation between these brackets A, image B, to denote the image of the controllability matrix. By the common rank condition that we already saw before, it holds that the pair AB is controllable if and only if this reachable subspace is the whole space, so Rn. I also define a notion of A invariant. So let's say that we have a subspace V of Rn. I call that A invariant if A times V is contained in V again. Meaning that if I take any vector from this subspace V, I multiply by A, then the resulting vector is still in the subspace. But there are some facts about this reachable subspace, namely it is A invariant and it contains the image of the matrix B. A invariance you can prove using the Cayley-Hamilton theorem. Because you know that A to the power n can again be expressed in terms of the lower powers of A. But you can prove a little bit more, in fact, that reachable subspace is the smallest subspace with the above two properties, meaning A invariance and containing image B. So what does smallest mean? Well, if I take any subspace V that is A invariant and that contains image B, then necessarily that subspace must also contain the reachable subspace. So in that case, we say it's the smallest one. Okay, then finally, we're also going to use this lemma. It's relating controllability of the pair AB to controllability of a pair of extended matrices. So let's have a look at these extended matrices. So I define for a given positive integer k, this matrix calligraphic AK over here. What is that? Well, it takes A, B, puts zeros here, and an identity matrix of size k minus 1 times n. And so this is an extended A matrix of size n plus km by n plus km. In addition to that extended matrix, I also define an extended B matrix, Bk, containing zeros, and finally an identity block of size n. So this is a matrix of size n plus km times n. The statement of the lemma is the following. So AB is controllable if and only if this pair of extended matrices AK, Bk is controllable. You can prove that by looking at the common rank condition of this pair AK, Bk. And that's also something we're going to use in the proof. Okay, now let's go into the proof of the fundamental lemma. The first thing I want to prove is the following claim. So I will use some shorthand notation to denote this Hankel matrix with one row of states and k rows of the inputs. And I call that the matrix Jk. I can define that for k1 up to n plus L. What is the statement of my claim? Well, let's assume that the rank of Jq is less than n plus mq, meaning that the matrix Jq does not have full row rank for some q. Then it turns out that in fact Jk does not have full row rank for all k larger or equal to q, right? So for k, q plus 1 up to n plus l, also jk does not have full row rank, meaning that the rank of jk is less than n plus mk. Now, that's my first claim. Now let's try to prove that. So I'll do it on the board here. So I'll prove the claim by induction. So I let, first of all, k be in this set. q plus 1 up to n plus l. And I'm going to assume that jk does not have full row rank. So rank of jk is less than n plus mk. My goal is to prove then that also jk plus 1 does not have full row rank. And then the claim follows by induction. If jk doesn't have full row rank, the next one also doesn't have full row rank, and so on. So to prove, also the rank of jk plus 1 is less than n plus m k plus 1. Okay. Well, using the assumption, I know that there exist vectors, let's call them psi and eta 1 up to eta k in Rm. Not all 0. Such that if I put all these vectors together in one row vector, so I look at psi transpose eta 1 transpose up to eta k transpose, and I multiply now by the matrix jk, I get 0. Right? Because we assume that jk does not have full row rank, so there must exist some non-trivial linear combination of the rows of this matrix adding up to 0. So these psi and eta 1 up to eta k, they're not all equal to 0. Okay, good. Well, what does this imply? Well, remember, I want to prove that also jk plus 1 does not have full row rank. So what I'm going to look at now is psi transpose, eta 1 transpose, up to eta k transpose, and I put a 0 vector behind that of size 1 times n. This row vector I'm going to multiply with jk plus 1. Well, let's have a look what we get then. Well, this is of course psi transpose eta 1 transpose to eta k transpose 0 times this matrix jk plus 1. That was this Hankel matrix with one row of states. And k plus 1 rows of inputs. Like this. All right, so one row of states, k plus 1 rows of inputs. Well, because of this 0 block, I'm going to cancel the last row of inputs. So this whole thing is going to be equal to psi transpose eta 1 transpose up to eta k transpose times x0 up to uk minus 1 here. So x0, u0 up to uk minus 1, and then the remaining columns of this matrix. Like this. So question for you. What do we know about this product that I wrote down here? Let's have a look first at this matrix on the right here. So what you see here are all columns of the matrix JK, right? Because we have one row of states now, and exactly k rows of the inputs. In fact, this is just the matrix JK with the last column removed, right? Well, we assumed that this psi eta 1 up to eta k transpose times JK is 0. So also, this must be equal to 0. Again, this is a submatrix of JK. That's the point. So that means that indeed, we have found a non-zero element in the left kernel of this matrix JK plus 1, which implies that indeed the rank of JK plus 1 is less than n plus k plus 1 times m. And that proves then the claim by induction. So, the point is that using this claim, we conclude the following. Yeah, that could be the case indeed. Yeah. But of course, when we want to prove this claim, we only need to show that there exists one. Yeah, but there could be others. That's true. Yeah, indeed. Other questions about the proof? No? Okay. So the point of the claim is the following, right? So assuming that this JQ matrix does not have full row rank, then all deeper Hankel matrices, so for K, Q, Q plus 1, and onwards, also do not have full row rank. That's the point. That's what we proved. Okay. Well, let's make some space for the next part of the discussion then. Okay. Next. Now we want to prove item 1 using this claim. So, remember, item 1 using this notation now can be reformulated as follows. So I want to prove that the rank of JL is exactly equal to n plus ml. I'm going to prove that by contradiction, so let's assume that that is not the case. I suppose that the rank of JL is in fact not equal to n plus ml, and then of course it must be less than n plus ml. By the claim, it then follows that the rank of JK must be less than n plus mk for all k larger or equal to L. And that's what we just proved. So let's now continue on the board again. So, we have the following situation. The rank of JL, we suppose that was less than n plus ml. On the other hand, if I continue increasing the depth of this Hankel matrix up to the matrix JN plus L, then the rank of that matrix JN plus L must be larger or equal to n plus L times m. Can you see why that is the case? So why is it the case that the matrix JN plus L must have rank larger or equal to n plus L times m? That's due to an assumption we made in the fundamental lemma. particular, because we assume that the input U is persistently exciting of order n plus L, the input Hankel matrix must already have rank larger than n plus L times m. Meaning if I put the row of states on top of that, of course also the matrix J n plus L must have rank larger or equal to n plus L times m. And so this last inequality, it follows from the assumption of persistency of excitation. That's the point. Okay, but now let's have a look. So by increasing this depth like this, you see that we obtain a certain rank difference here. Right, so there's a rank difference. And the rank difference in particular is, well, it's larger or equal to m minus 1 times n plus 1. Right, because JL has rank less than n plus ml, and Jn plus L has rank larger or equal to n plus L times m. That means that there must exist some k, a number between L and n plus L minus 1, such that, in fact, the rank of jk plus 1 is equal to the rank of jk plus m. Why is that the case? Well, you see that this rank difference must be at least this number over here. Suppose that the rank only increased by m, at most m minus 1 at every step here. Then I would add only m minus 1 times n to the rank in this process. But since we know that the rank difference is at least m minus 1 times m plus 1, there must be one rank increase here in this process of m. That's the point. So there must be these matrices, jk plus 1 and jk, whose rank have a difference of exactly m. Otherwise, I cannot get this rank difference over here. Okay, good. Now I continue. What I do now is I look at the image of the matrix jk plus 1. My goal is to prove that the image of jk plus 1 is ak plus 1 invariant and also contains the image of bk plus 1. And then we're going to use controllability. Remember, the fundamental lemma had these two assumptions: persistency of excitation and controllability. Persistency of excitation we have already used here, and now we want to use also the controllability. So, I'm going to work out this image of jk plus 1. What is this? Well, this is the image of this particular matrix, right? So I write it down again. x0 up to x t minus k minus 1. u0 up to u t minus k minus 1. Up to u k minus 1, uk. And we complete this up to ut minus 1, ut minus 2. Like this. So this is the matrix jk plus 1. Okay. Maybe I can use a different color here. Because if you look now at the submatrix of this matrix, in particular the one over here, so I exclude the last part, so the last m rows of this matrix, then these are all columns of jk. Right, again, because we have here a Hankel matrix of inputs of depth k. Which means that this image of this jk plus 1 matrix must be contained in the image of jk cross Rm. Okay? But we also know something about the relation between the ranks of jk plus 1 and the rank of jk. So let's have a look at the dimensions of the subspaces that we see over here. The dimension of the subspace over here, the image of jk plus 1, is obviously equal to the rank of jk plus 1. Well, what is the dimension of the subspace that we see here on the right? Well, the dimension is just the rank of jk plus the dimension of Rn, which is m. By the formula that we had over here, the dimension of this subspace must thus be equal to the rank of jk plus 1. Meaning that we have one subspace contained in another subspace. They have the same dimension, so they must be equal, in fact. So this implies, in fact, that the image of jk plus 1 must be equal to the image of jk Cartesian product Rm. Very nice. Okay, good. Now I continue. I'm going to work out now the product calligraphic AK plus 1 times JK plus 1. Like this. So what was this again? Well, the AK plus 1 was this extended A matrix. So AB, zeros, 0, 0, identity Km, 0, 0, 0. Right, and furthermore, the JK plus 1 matrix we already had before. So this was x0, u0, up to uk minus 1, uk. Like this. So let's compute what this product is. We have a very nice system here, so I can just create some extra space by writing here on the right. So I work out this product. What is this? Well, let's first have a look at this first column over here. So I'm multiplying A with x0, B with u0, so I'm creating x1 here. Right, so I create x1, then u1 up to uk with zeros. And the u1 up to uk comes from the fact that I have this identity block over here. So the u1 up to uk that appear here are just multiplied by identity. And then finally I get the 0. So I continue this matrix up to x and u t minus k, and ut minus 1, like this, and then the one final row of zeros. Okay, great. Well, let's again have a look at only the first part of this matrix. Also, this first part of this matrix is again a submatrix of the matrix JK. In fact, if I remove the first column of the matrix JK, then this is exactly the matrix that I obtain, right? Because I remove the x0, u0, etc. from that. So these are all columns of JK. Okay, what's the point of that? Well, that implies that if I look at this calligraphic AK plus 1 multiplied with the image of JK plus 1, right, that's going to be in the image of JK cross Rm. Yeah, but we knew already something about the image of JK cross Rm, right? Because that was the image of JK plus 1. Great. So this is the image of JK plus 1. AK plus 1 times the image of JK plus 1 is contained in the image of JK plus 1. In other words, image of JK plus 1 is AK plus 1 invariant. Fantastic. So, for the final part of the proof, I also want to show that the image of BK plus 1 is in the image of JK plus 1. And then finally, we're going to use controllability. So let me first write down what BK plus 1 was again. Since BK plus 1 was equal to this matrix, so 0, 0, identity of size M, we obviously have that the image of BK plus 1 must be in the image of JK cross Rm. Right, because the image of identity matrix is here, and 0 is in the image of JK. But again, now I'm going to use the fact that the subspace that we see over here is just equal to the image of JK plus 1. And then indeed, you see that the image of BK plus 1 is contained in the image of JK plus 1. Great. Okay. So, this means that the image of JK plus 1 is an AK plus 1 invariant subspace containing the image of BK plus 1. But the reachable subspace of the pair AK plus 1, BK plus 1 is the smallest A invariant subspace, AK plus 1 invariant subspace containing the image of BK plus 1. So this also implies that the reachable subspace of the pair AK plus 1, BK plus 1 must be contained in the image of JK plus 1. Now, that's great. I just need a little bit more space. Because what is the point now? Well, we had that AB is controllable. And by the lemma on the slide, that also implied that the pair AK plus 1, BK plus 1 is controllable. So the reachable subspace must be the whole space, obviously. Right, so AK plus 1, image bk plus 1 is the full space, namely Rn plus m times k plus 1. Which means that the full space must be contained in the image of jk plus 1. Aha. That must imply then that the image of jk plus 1 is the full space. So then the rank of jk plus 1 must be equal to n plus m k plus 1. But that's a contradiction. That's a contradiction because by our claim, the rank of jk plus 1 must be strictly less than this number over here. Right? So indeed, we reach a contradiction, and that means that finally we have proved that indeed the rank of JL must be equal to n plus ml. Great. And then we have proved, indeed, item 1 of the fundamental lemma. Okay. Before we continue, are there any questions about this proof? Yes? Sorry, for the J matrix, you said? Okay, so in this proof, I'm reasoning with the state of the system. But let's say in practice, you don't need to know that state. Right? I'm just trying to prove that indeed this rank condition holds. But in practice, you would apply something like subspace identification and you could identify actually the row space of a state sequence. Does that answer the question, or? Otherwise, we can also discuss offline. Other questions? No? Okay, let's yeah.
Is there a reason why we choose the depth 1 matrix for the anchor matrix for the state and depth k for the?
Yes, there is a very good reason for that, why we do that. The reason is that for the depth 1 Hanko matrix of the state and this depth k Hanko matrix of the inputs, there's a very nice relation with the depth k Hanko matrix of both the inputs and the outputs. So you need to work with the depth 1 Hanko matrix of states. Yeah. Yeah, indeed. Yeah, indeed. So that's also a good observation, indeed. So let's see. Yeah, when we, or maybe I erased it already. We use indeed in this AK plus 1 matrix, right? You have the A and B next to each other. You multiply with this one row of states, and then you create actually a new row of states. And that's indeed one of the main ideas. Yeah. Mm-hmm. Yeah. Okay. Well, let's continue. And what I want to do now is, I do not want to go in all of the details, but I want to discuss some applications of this fundamental lemma, without showing you any of the proofs. First, starting with this paper by Ivan Markovsky and Paolo Rapizarda. So they studied the data-driven tracking problem that I want to explain next. So the problem is as follows. Let's suppose that we have two integers, L_ini and Lr, both positive, and let's define L to be the sum of those. We're considering a positive semi-definite matrix, Q, which is going to be the weight matrix in our tracking problem. We'll also have access to the data, similar as before, and now an initial trajectory of the system. So U bar, Y bar on the time interval 0, L ini minus 1. I will come back to why that initial trajectory is important in a second. Finally, I also have a reference signal on the time interval L ini to L minus 1. And the goal is to use the data to come up with a control algorithm that tracks this reference trajectory. So we'd like the inputs and the outputs of our system to track this trajectory. In particular, how we want to do that is we want to find a trajectory of the system in such a way that we minimize this cost function over here. So essentially this cost function is measuring the difference between the trajectory of the system, u bar y bar, and the given reference trajectory. And so we want to minimize that cost function, of course subject to the constraint that we have a valid trajectory of our linear system. So subject to the constraint that u bar y bar is in the restricted behavior of the system. That's the goal. So let's have a look at the picture just to make this a bit more clear. So here I just plot only the outputs. You can have a similar plot for the inputs. So the outputs are already given on this initial trajectory from 0 up to L ini minus 1. And then in the future, so from L ini up to L minus 1, we have a given reference trajectory, z. And then when I want to find the y bar trajectory in blue, that closely tracks that reference trajectory. And similarly for the inputs of the system. That's the goal. Now, you may have a question like, okay, why do I include this initial trajectory? Of course, you could also leave it out and just focus on an input-output trajectory on only this interval. This problem is a little bit more general if you include an initial trajectory, and essentially it is to fix the initial conditions of your system. And so here we only work with input-output data, so we cannot simply specify like x0 must be something, right? But if you choose this L ini sufficiently large, in particular larger than the leg of the system, then you can fix the initial condition of your system by choosing a suitable initial trajectory. So that's why it's included. Okay, so how do we solve this data-driven tracking problem? Well, again, we construct a Hankel matrix of the input and the output, and similar to the subspace identification story, we partition that Hankel matrix in UP, UF, YP, and YF. In this case, the UP has L ini block rows, and the UF has LR block rows. So L ini and LR do not have to be the same like we had in the subspace identification. So it's a bit more general. Okay, now what's the point? This is actually the main idea of this data-driven tracking. Because of the assumptions of the fundamental lemma, so let's assume that AB is controllable and the input is persistently exciting, like we had before, we can replace our constraint, namely that the U bar, Y bar is in the restricted behavior, by a constraint like this. So the U bar, Y bar trajectory must be in the image of the data Hankel matrix, right? So it must be the data Hankel matrix times some vector G. And the idea is to formulate this data-driven tracking problem now as an optimization over this vector G. That's the goal. Now, in particular, what one can show, again, not showing all the details, but if you define this extended Q matrix, Q tilde, which I did here on the slide using what's known as a Kronecker product. So we have the Kronecker product of identity with Q11, and so on. Then you can reformulate this data-driven tracking problem as this constrained least squares problem. So you minimize the cost function over this unknown vector G now. The cost function depends only on the Q, so the weight matrix in your tracking problem, the data matrices, UF, YF, and the reference trajectory, VZ. And the constraint also only depends on the data and the initial trajectory that is given. So the point is that using the fundamental lemma, you can very nicely incorporate this constraint that this trajectory u bar y bar must be a restricted trajectory of the system. Now, this constraint least squares problem you can solve using standard methods, so that is not complicated at all. For instance, you could introduce Lagrange multipliers and solve a system of linear equations to solve that.
What V stands for which signal you are referring to this V?
Ah.
This is a reference signal, but
Yeah.
that is being compared with Y, so that makes sense. But this V is specifically subtracted from U. So is it an ideal control which you are trying to specify?
So the V is the reference signal for the inputs. So I'd like to track both an input and an output trajectory. So in particular, I'd like to make the difference between the inputs and the V small and the outputs and the Z small. So it's an input-output trajectory that you're specifying as a reference. If you don't want to do that, you could also consider a specific problem where you only measure the difference between Y bar and Z. So only specify the difference between the outputs. Does that somewhat answer your question, or?
Because sometimes we may not know V.
Yes, yeah. So in this case, we do assume it to be known. Yeah. But again, as I said, you could also consider a specific case. If, for instance, this Q is of a specific form, like 0, 0, 0, and then some matrix, you could just impose a constraint only on the outputs, right? So yeah, you can handle that.
So just as a follow-up.
Yeah, sure.
In a practical setting,
Yeah.
what would V mean? Take any practical example. Let's say you want to control a mass spring system.
Mm-hmm.
So in that case, what would V mean? V.
Yeah,
Reference input.
Yeah, it's just some given input-output trajectory. Yeah? This VZ, it could be anything that you desire to track.
From behavioral perspective, so some input-output trajectory that is present in the behavior.
Yeah, yeah. Okay. Well, that was a paper by Markowski and Rapizarda. Actually, that was used in a follow-up paper that came much later in 2019 in a predictive control setting. So the idea is to solve a receding horizon control problem, where at every time step you repeat to solve this finite horizon tracking problem. Not necessarily. The point is that, of course, yeah. Yes, yes.
And why is it?
Yes. Well, of course, it's not necessary to specify beforehand that the Vz is a trajectory. If it's not a trajectory of the system, then I cannot make this cost function 0 in general. But I can still try to minimize it. So for instance, in this example on the slide here, I'm also not tracking exactly this reference trajectory, right? Which means that, depending on the matrix Q, of course, I'm not making this cost function exactly equal to 0. But I can still try to track it approximately. So it's not specified beforehand, but of course you could apply it to the situation where Vz is a trajectory, valid trajectory of the system. And that would definitely make sense, of course.
So this kind of a controller would lead to an open loop?
Open loop, yes, indeed, yeah. Yeah, so you're computing a trajectory, input trajectory of the system. Yeah, that's indeed, okay. In this follow-up work on predictive control, you solve that in a receding horizon fashion. And that's actually a kind of way of creating feedback, because you repeat this computation of this open loop controller. Yeah.
You can impose some constraints on
Yeah, indeed. That's not something I showed here, but that would lead to additional constraints in this problem. That's true, yeah. Yeah, and in the predictive control literature, that has been studied a lot indeed. Yeah, that's true. Exactly, yeah. So of course, indeed, if you choose them very wildly, then the tracking may be very bad indeed. Yeah. Yeah. So indeed, it makes sense also to choose them as trajectories of the system. Yeah. Okay. So about this follow-up work, again, I already explained the idea a little bit. So this was the work by Coulson and co-authors. The idea is to repeat this computation of this finite horizon tracking problem and to make it into an online procedure. So again, we have given data, the weight matrix Q, some initial trajectory of the system, and a reference signal. The important difference here is that the reference signal is now defined on the time window from L ini to infinity, and not on a fixed finite length time window. So we start by setting time tau 0. And the idea is now to compute a trajectory that again predicts LR steps in the future. So I compute this U predicted and Y predicted that solve again this tracking problem. So I solve the same cost function as before. Again, want to make the predicted UY trajectory close to the reference, subject to the constraint that this whole trajectory is in the restricted behavior. The idea is then to only apply one step of the input that I just computed, right? Because here I compute the whole sequence of inputs on this time window. I apply just the first one to the system, and I measure the corresponding output. And then the idea is to repeat the procedure. So I set tau to be tau plus 1, and I again go to step 2. So again, I compute this finite horizon tracking problem, and I repeat the process. Coulson and co-authors showed the equivalence with model predictive control under suitable assumptions. So in particular, you need to assume the controllability and persistency of excitation conditions of the fundamental lemma. And also the L ini needs to be larger than the lag of the system. Well, as was mentioned already before, indeed it's possible to include also constraints on the inputs and the outputs of the system. And there are also regularization methods to deal with noisy data. And finally, there's some follow-up work by Julian Berberich, who studied stability analysis of these data-driven predictive control schemes under some terminal constraints. Okay. So then, after the data-enabled predictive control, we continue with another application of the fundamental lemma. This was by Claudio de Pezes and Pietro Tesi in a paper from 2020 on formulas for data-driven control. And they established actually a kind of data-based closed-loop parameterization. In their paper, they mainly focus on input-output data. Sorry, on input-state data, so not input-output. So we have just the input-state dynamics, xt plus 1 is ax plus bu. And for now, we consider the case of input-state data. So I use a shorthand notation. X denotes the Hankel matrix of depth 1, so just one row of states. And U minus denotes the Hankel matrix of depth 1 of the inputs. We also define shifted versions of the state data. So X plus denotes the Hankel matrix of depth 1 of the states, starting from time 1, so I exclude the X at time 0. And X minus starts at time 0 and goes to t minus 1. Note that by defining these shifted state matrices, we of course have the following relation, that the shifted states starting at time 1 are A, B times X minus U minus, the states and inputs at the previous time. right? Well, what follows from the fundamental lemma is the following. So if we assume that AB is controllable and U is persistently exciting of order n plus 1, so we take the L in the fundamental lemma to be 1 here, then the rank of the input state Hankel matrix, where I just have one row of inputs, right? So capital L is 1, is full. It's n plus m in this case. That's a direct corollary of the fundamental lemma. So what Claudio and Pietro then did was the following. So they argued in the following ways. Well, since this matrix then has full row rank, for any feedback controller, U is Kx, there must exist some matrix G that satisfies this system of linear equations. And so I can write identity over K as x minus over U minus times this G. And the idea is now to see this G as the design variable instead of the K. So in particular, they use that to obtain this database representation of the closed loop system. So under this control law, if I plug that in to the system, right, I get xt plus 1 is a plus bk times x. I write that as ab times I over k times x of t. But since I over k is related to the data in this matrix G, I can plug that in over here. And you see that indeed then xt plus 1 is x plus times G times xt. And this is what they call a database representation of the closed loop system, because the closed loop system matrix in this case is just x plus times G. So it depends on the data, x plus, and this design parameter G that we can still tune. There are different problems they considered then in their paper. One is stabilization. So there the goal is then to choose this G in such a way that x plus times G is stable. Yeah? So indeed, using the data, you create then a stabilizing controller.
Is there any extension for this work for the eigenvalue assignment problem, or only stability?
Yes, yes, there is also some work on eigenvalue assignment indeed. Together with Andrea Bisoffi, they considered that problem indeed. Yeah. We also have some work on that, for instance, deadbeat control, where you want to make this matrix nilpotent. We'll see that also in the rest of the course, actually. That will be nice. Yeah. Other questions about this?
X plus is constructed with a certain length of data.
True. Yeah, it is exactly T.
Does it get updated as you get more and more data?
No. In this approach, it's purely offline. So we collect one batch of data, and then we construct a controller. Yeah. So indeed, that's different from the predictive control, where you could also include the additional data in principle. Although in the first papers, they did not also do that. So it's always from one batch of data, you construct a controller. Yeah, okay, so indeed, that's also possible. That's indeed something we worked out together with Harry Trentelman. So we studied the tracking problem there also. Yeah, that's possible. Okay. Well, to kind of summarize the lecture of today, what have we seen? Well, starting from the fundamental lemma, always the assumption has been controllability of your system and persistency of excitation of the input. And we've seen that we can do, under these assumptions, many things, right? We can do subspace identification, so we identify A, B, C, and D up to the similarity transformation. We can do data-driven tracking directly from data. An extension of that was data-enabled predictive control. And finally, we also saw this paper on closed-loop parameterization. But this is all under the assumption that the input is persistently exciting, which also puts this quite conservative lower bound on the number of data samples that you need. Right? So you need a fairly large data set to have inputs that are persistently exciting. So interesting question is the following. Can we find controllers even in situations where the input does not satisfy that persistency of excitation condition? That would be very interesting. And yeah, maybe you're very critical students, of course. I started out my story this morning by saying that we want to do direct data-driven control, avoiding subspace identification or some other means of identifying the system. But for the methods that we've seen today, you could ask a very critical question like, yeah, couldn't I just first identify a system and then do just model-based tracking, for instance, right? And under these conditions of PE, the answer is yes, you could do that. But the very interesting question is the following. So in situations where I do not have persistency of excitation of the input, and perhaps I cannot uniquely identify a model, can I still do control? At least for some control problems. Or can I still maybe identify certain system properties that my system has? That would be very interesting. Also, this is something I stressed before, so indeed, this persistency of excitation condition that puts a lower bound on the number of data samples. But what is the minimum number of data samples that I need for a certain control task, like stabilization or tracking or something else? That's not clear at the moment. Persistency of excitation is certainly sufficient to do these things, but it may not be necessary. And then finally, what about noisy data? So far, we assumed that the data was always this restricted trajectory of the system. And there was no noise, right? We measured exactly this trajectory of the system. But in practice, we may have noise on the data. And how to deal with that? So all of these questions we're going to, we will address in this course. But before we can do that, we really need a new framework for data-driven control. And that's going to be the topic of day 2. So tomorrow, Kanat is going to start by talking about this paper on data informativity. And he will introduce this new framework to study data-driven analysis and control problems. So that brings me to the end of today's lecture. Let's quickly recap. So I've attempted to give you this historical perspective by talking about subspace identification and then the fundamental lemma, and these direct data-driven control approaches that use the fundamental lemma. Tomorrow we will introduce the data informativity framework to deal with data that are not necessarily persistently exciting, and to also find controllers in situations where system identification is not possible. Then on day 3, we will even continue with that to talk about noisy measurements. And we will also use the data informativity framework for that. So that's the end of today's lecture. I want to thank you very much for your attention. Thank you. Yeah, of course.
So in many places we are computing the rank of Henkel matrix and all these places.
Indeed.
So and based on each rank, we are taking some decision that what will be the system order and all these things. So how sensitive is it numerically when we are computing the rank? And the decision that we are making on this system point of view.
So numerically, you would always compute a rank using singular value decomposition. So you make a singular value decomposition of your data, Hankel matrix, and then there's a certain threshold, right? So you need to decide, I don't know, your threshold is 10 to the minus 12 or something. All of the singular values which are larger than that, you count, and then you decide that this is a rank. Of course, these computations are indeed sensitive to noise. In the sense that if I have an additive perturbation to u and y, very often what happens is that the rank is already going to be the maximal rank, right? So all of the things that I've talked about today, I would say are mainly focused on a noise-free data case. So in the noisy case, we really need different approaches to ensure robustness against the noise. And yeah, there are certain tools that we can use for that, like matrix S lemma, and we'll talk about that on day 3. Indeed, it's a good question. So it's indeed true that these ranks are sensitive to noise. So if you have noise, then the rank is going to change, indeed. Yeah.
Is there any merit in studying extension to continuous time?
Yeah, definitely. There are several extensions. In fact, together with Paulo Rapisada, we also extended the fundamental lemma to continuous time systems. Yeah.
And also, the underlying assumption so far has been linearity and time invariance.
True.
So, can we relax the assumption?
Yeah, there are also certain works that work with classes of nonlinear systems. Typically, the assumption there is that you have some linear combination of known basis functions. So you assume the nonlinear basis functions, you just don't know what kind of linear combination creates the vector field of your unknown system. And there have been extensions to, for instance, classes of polynomial systems. Luret systems have also been studied. So there indeed have been some extensions. I do think, though, that in general theory, for general nonlinear systems is not there. So it's for classes of nonlinear systems. Yeah, that indeed. In the paper on quadratic matrix inequalities, we also study that, indeed. You have some sector bound on your nonlinearity, and then you can find controllers that are absolutely stabilizing. Thanks.
Majority of the work, I think we needed to know at least the order of the system.
In this case, no. So we need to know something about the order of the system. So for instance, in the subspace identification, right? We assumed this upper bound on the state space dimension.
Data-driven control and the predictive control. The application which you shared,
you can also work with this upper bound. The difference is that then you don't need persistence of excitation of little n plus L, but capital N plus L. So you can extend these data-driven control methods to this upper bound. Yeah. But the point is that if you have persistency of excitation of order capital N plus L, you also have it for little n plus L. So in fact, you can work with this upper bound.
We have the data for a system whose order is at least known to us.
Mm-hmm.
Say U and Y pairs are known. Can't we simply use the least square method in order to estimate the, say, difference equation or differential equation?
True. That could also be, yeah, indeed. So if you know the order, you could also focus on identifying an AR model, autoregressive system. Or, in behavioral theory, this is called kernel representation of your system. That would be an alternative approach to the subspace identification, indeed. Indeed, the idea of subspace identification is to identify a state space model, but there are, of course, other representations of your system. That's true, yeah. Yeah. But the point is that you want to identify the true system up to this similarity transformation. And there you do actually use observability. Well, okay, so I also did not go through the proof of this subspace identification. So the point is actually that there's a relation between the state input Hanko matrix and the input output Hanko matrix. And to say something about the rank of the input output Hanko matrix, you do actually use observability. Yeah, because the observability matrix appears in that relation. Yeah. No, sure. No, it's good. Yeah. Yeah. So indeed. Yeah, so the point is, indeed, if you don't have observability, then there exists some lower order state space system. So then also you cannot identify n, really. Yeah? That's another point indeed to look at. Yeah. Yeah. So as for this relation between the input-output Hankel matrix and the input-state Hankel matrix, so one relation you can prove is that. So if I just look at the vector of output, let's say like this. This is related to the observability matrix. Times the initial state of your system, plus what is known as a tuplets matrix of Markov parameters. So that's D on the diagonal, CB up to C to the power L minus 2B, like this, and zeros above the diagonal, times the inputs. If you want to do that for a Hankel matrix, you just put multiple columns here, and then a similar relation holds not with x0 but with x1 and so on. But this relation is often used in the subspace identification literature, and you see that here indeed the observability matrix comes into play. No, you don't need it. No, indeed. It's because you want to track an input-output trajectory of the system. So indeed, you don't need observability. Yeah, good question.
That condition might have been imposed in the rank condition for Hankel matrix. That conditions might map to some rank condition in the computation.
So without observability, indeed, you do not have the same rank condition on the input-output Hankel matrix, but still, you can parameterize all input-output trajectories of the system using the fundamental lemma, because the fundamental lemma does not require observability. And these direct data-driven control methods, they directly use that parameterization of the fundamental lemma. So also there, you don't need observability. Yeah, so here, yeah, I see your question. But here really it's a prior knowledge. So you assume a priori that AB is controllable. Yeah. Yeah. Indeed, it's going to use this relation also, indeed, yeah. Sorry, maybe it would be? It's capital N. You mean in the second problem of the problem-solving session? Yeah, indeed. Yeah, definitely. So, okay, maybe to give some context. the second problem, in the problem-solving session, I just give you some input-output data, and you try to identify this state space dimension N. You have an upper bound, which is 7 in that problem. I can already reveal that the true state space dimension is not 7. It's going to be larger. But you try to identify what is this N in that problem. Yeah, thanks. All right. Yeah, thank you all again.
So I
Yes, for the second problem you need indeed.